In this video, we're going to go through the computation of all the tensors related to the FLRW metric. In the last video, we derived the FLRW metric, which is like three metrics in one for the three possible spatially homogeneous and isotropic universes. These are universes where all spatial points look basically the same, and all spatial directions look basically the same. The three possible universe geometries are the closed universe, the flat universe, and the open universe, provided that we're ignoring more complicated geometries that have holes. In the FLRW metric, we can choose between the three geometries by selecting the parameter k to be +1 for a closed universe, 0 for a flat universe, or -1 for an open universe. In this video, we're going to derive all the tensors and coefficients related to the FLRW metric, so that we can see how the universe will evolve according to the Einstein field equations. So this video is going to be very computation heavy and a bit boring, but it's necessary for future videos where we will look at the motion of free particles in an expanding universe and derive the Friedmann equations. Before I start, I'm just going to mention some notation. When a tensor summation is written with Greek letters, this refers to a summation over all four spacetime indices, where the index 0 is time ct, and 1, 2, 3 are the spatial coordinates r, theta, phi. If a tensor summation is written with Latin or English letters, this just refers to the three spatial indices only. Also, even though the universe scaling factor a of t depends on time, I'm just going to write it as a to save space. The first derivative of a with respect to time will be written a dot, and the second derivative of a with respect to time will be written as a double dot. Finally, since all the spatial components in the metric are different factors multiplied by a squared, I will sometimes write these spatial factors using lowercase gamma. So the spatial metric components are a squared times the gamma components, where the gamma components are defined here. So let's start by calculating the inverse metric for the FLRW metric. Getting the inverse metric is easy since the inverse of a diagonal metric involves just taking the reciprocal of all the diagonal elements. So given the components of the metric and the inverse metric, let's compute all the connection coefficients. Since our metric is diagonal, we know that the two indices on this inverse metric must be the same, so we can change the alpha indices to sigmas. This is not a summation over sigma on G inverse. This is just a repeated index. The summation is with the lowered indices on all the g's inside the brackets. Let's start by calculating all the connection coefficients with a 0 index up top. For 0, 0 on the bottom, these two terms inside the brackets cancel. We're going to see a lot of canceling inside these brackets in this video, so I'm just going to do the canceling without saying anything out loud from now on. We're left with a derivative of g00. And since g00 is constant, it goes to 0. Now let's look at the case where both lower indices are spatial indices that are repeated, denoted by the index I. Metric components that have one space index and one time index are off the main diagonal and they go to 0 for the FLRW metric. G inverse 0, 0 is +1. And the time derivative of -GII is just the CT derivative of -a squared times gamma II. Since only a depends on time, and not the remainder of the spatial metric components gamma II, the derivative of a squared becomes 2a times a chain rule term. We can cancel the 1/2 with the 2 and rewrite the time derivative of a as a dot to get this. So given this formula and plugging in the three different values for gamma II, we get three connection coefficients where the lower indices are 1, 1, 2, 2, and 3, 3. In each case, the negative signs cancel, and we get three connection coefficients which start with a dot over c, and then have a second factor that's different depending on the spatial index. It turns out that all the other connection coefficients with a 0 index on top go to 0. Let's continue on with the connection coefficients that have a 1 on top. For the case with 0, 0 on the bottom, all the metric components are either off-diagonal or constant, so this goes to 0. For 1, 1 on the bottom, these cancel and we get 1/2 inverse g11 times the 1 derivative of g11. Since the 1 index is r, we get this times the r derivative of this. Since the scale factors a only depend on time, we can take them out of the derivative and cancel a squared. To take the r derivative of this, we use power rule to give the denominator a power of 2, and then get a chain rule term of negative 2kr. The negatives cancel, the 1/2 and 2 cancel, and 1 power of 1 minus kr squared cancel, so we get kr over 1 minus kr squared. For 2, 2 on the bottom, off diagonals cancel, and we get the r derivative of g22. We again cancel the a squareds, since they only depend on time, and the r derivative of r squared is just 2r. Canceling 1/2 and 2, we get negative 1 minus kr squared times r. For 3, 3 on the bottom, off diagonals go to 0, and g33 is the same thing as g22, but with sine squared on the end. So we get the same coefficient, but with sine squared on the end. Next, we'll look at 0, 1 on the bottom. Off diagonals go to 0, and after plugging in, we get the time derivative of g11. The 1 minus kr squared factors cancel, and the derivative acts on a squared to give 2a dot. And canceling, we get 1 over c times a dot over a. And since the lower indices of the connection coefficients are symmetric, gamma 101 equals gamma 110. It turns out that all the other connection coefficients with a 1 on top go to 0. Next, let's look at the connection coefficients with 2 on top. If we look at the cases with 0, 0, 1, 1, and 2, 2 on the bottom, after setting the off-diagonal terms to 0, we just get the theta derivative of expressions that don't involve theta, so they all go to 0. However, with 3, 3 on the bottom, the off-diagonals go to 0, and we get the theta derivative of a term that does involve sine theta squared. After taking all the non-theta terms out, they cancel with each other, and the derivative of sine theta squared becomes 2 sine theta times cosine theta. Canceling 1/2 and 2, we get that gamma 233 equals negative sine theta times cos theta. For 0, 2 on the bottom, we remove the off-diagonals and sub in. We can take the r squared out of the time derivative and cancel it. And the time derivative of a squared is 2a dot. After more canceling, we get gamma 202 and gamma 220 is 1 over c times a dot over a. For 1, 2 on the bottom, we get rid of the off-diagonals, sub in, cancel, take the derivative, and get 1 over r. And for 3, 2 on the bottom, we get 0. So these are all the non-zero connection coefficients with 2 on top. All the others go to 0. Finally, we'll look at the connection coefficients with 3 on top. If both lower indices are the same, we end up with a phi derivative. And since none of the metric components depend on phi, all of these go to 0. For 0, 3 on the bottom, we can plug in and see that we get a time derivative. The factors that don't depend on time all cancel, and the time derivative of a squared gives 2a dot. More canceling gives us 1 over c a dot over a. For 1, 3 on the bottom, we plug in, and all the terms not involving r cancel with each other. We end up with 1 over r. For 2, 3 on the bottom, all terms not involving theta cancel each other out. And we end up with cos theta over sine theta, which is equal to the cotangent of theta. all the other coefficients with 3 on top go to 0. So we've calculated all the non-zero connection coefficients for the FLRW metric. Now that we have all the connection coefficients, it's time to calculate the Ricci tensor components. The Ricci tensor components are just the Riemann tensor components, where we sum the upper index with the lower middle index. Let's start with R00. Thankfully, 2 of the connection coefficients go to 0 right away. We're left with a bunch of summations in the remaining terms. For the first summation, mu can be set to 1, 2, or 3 to give non-zero terms, since the mu equals 0 term ends up going to 0. For the second terms, there are only a small number of coefficients with 0 as the lower index. So this expands to a set of 3 terms, where we set both mu and beta to either equal 1, 2, or 3. Now, note that these are actually the same term repeated 3 times, and these are also the same term repeated 3 times. So I'll just write the terms once and put a multiplying factor of 3 out in front. Subbing everything in, we can factor out 1 over c squared to the front. Then we'll take the time derivative of a dot times a to the negative 1, which is done with product rule. The derivative of a dot becomes a double dot, and the derivative of a to the negative 1 becomes a to the negative 2 with a negative 1 out in front times the chain rule term of a dot. Notice that these positive and negative terms cancel, so we're left with R00 equals negative 3 over c squared times a double dot over a. Now, the 1, 1, 2, 2, and 3, 3 components of the Ricci tensor are all very similar to each other. So I'm going to get the basic formulas for them involving the connection coefficients, and then compare them and look for similarities. So R11 is defined by this formula. The non-zero terms in this summation are for mu equals 0 and 1. And for this summation, it's mu equals 1, 2, 3. This alpha goes over 0 and 1, and this beta goes from 0 to 3. These cancel, and these terms are equivalent, so I'll combine them and put a 2 in front. This summation has mu equals 1, 2, 3, but all those terms are equal, so I'll just write a single term with a 3 in front. This term goes over mu equals 1, 2, 3, but the 2 and 3 terms are equivalent, so I'll combine them together with a 2 in front. This is mu equals 1, this is mu equals 0, 1. This term has mu equals 2, and this term has mu equals 3. And these last 2 terms are equivalent, so I'll write them once with a 2 in front. This 3 cancels with these to give 1, and this cancels with this. Now, if we look at this term, this is the r derivative of 1 over r, which is negative 1 over r squared. And this term is 1 over r times 1 over r, which is positive 1 over r squared. So these terms cancel, and we're left with this formula for R11. Now, R22 is defined here, and these sums expand with mu 0, 1, mu 3, alpha 0, 1, and beta 0, 1, 2, 3. This mu sum expands to 3 of the same term. This mu sum expands to 1, 2, 3, but 2 and 3 are the same term, so I'll put a factor of 2 here. This mu must be 2, this mu must be 2, this mu expands to 0, 1, and this mu must be 3. This 3 cancels with these to give a 1, and this 2 cancels with both of these. So with this formula, this term turns out to be cotangent of theta squared, and this term is the theta derivative of cotangent of theta. Since cotangent is defined as cosine over sine, we take the derivative using product rule, and this ends up being negative 1 minus cotangent squared. So between these 2 terms, the cotangent squareds cancel, and we're left with minus negative 1, which is positive 1. So this is the formula for R22. R33 is defined here. This mu expands to 0, 1, 2, and this term goes to 0 since none of the terms depend on the third variable phi. Alpha expands to 0, 1, 2, and beta expands to 0, 1, 2, 3. This mu expands to 3 terms that are all the same, so I'll put a 3 in front. And this mu expands over 1, 2, 3, but 2 and 3 are the same term, so I'll put a 2 in front. Each of these mu's are forced to be 3, and this mu expands to 0, 1, 2. This 3 cancels down to a 1, this 2 cancels with these 2, and this cancels with this. Now, the last term is negative cosine times sine multiplied by cotangent, which is cosine over sine. So this is just negative cosine squared. And this is the theta derivative of negative cosine times sine. Pulling the negative sign out and using product rule, we get sine squared minus cosine squared. Since these two terms have opposite sign, the cosines cancel, and we're left with sine squared. So this is the formula for R33. So we have formulas for R11, R22, and R33. And immediately we see that the first terms in each case are zero derivatives of a coefficient with 0 on top. Notice that all of these coefficients start with a dot over c, and then are followed by the spatial terms in the metric for r, theta, and phi, which earlier we called the lowercase gamma coefficients. So the first terms each equal the time derivative of a dot over c times the gamma I for that index. The second terms also have this a dot over c gamma term, but multiplied by a coefficient equal to a dot over a times 1 over c. For this time derivative, we can pull c and gamma out in front since they don't depend on time. And using product rule, we get a double dot plus a dot squared. And for this term, we can cancel a's and simplify to a dot squared. Now, if we sub in the formulas into this term here, the r's cancel, and we can rewrite the denominator as gamma 1, 1 to get 2k gamma 1, 1. Next, notice that when we compare gamma 1, 2, 2 and gamma 1, 3, 3, the only difference is that gamma 1, 3, 3 has sine squared on the end. So we can change gamma 1, 3, 3 into gamma 1, 2, 2 if we factor out a sine squared. So now we just need to compute this expression. Subbing in, we see this cancels with this, and for this derivative, we need to use product rule. The derivative of this expression is positive 2kr, and this derivative goes to 1, so we just get 1 minus kr squared with a negative sign in front. Simplifying, we can cancel all these terms on the end to get 2kr squared. And since r squared is lowercase gamma 2, 2, we can rewrite this as 2k gamma 2, 2. And with the extra sign squared on the end, this is just gamma 3, 3. So these terms on the end each equal 2k gamma I. And I'll multiply and divide by c squared to make this consistent with the other terms. So all the diagonal components of the Ricci tensor equal this term in front, multiplied by the gamma I term from the metric, which gives these expressions here for I equals 1, 2, 3. And it turns out all the off-diagonal Ricci components go to 0, so we'll ignore them. So for the FLRW metric, we have the corresponding inverse metric, and we have the corresponding Ricci tensor components, which means we can calculate the Ricci scalar, which is just the trace of the Ricci tensor where one of its indices is raised using the inverse metric. If we plug all these terms in, we'll leave the first term alone. For the second term, we'll cancel 1 minus kr squared from both terms. For the third term, we'll cancel r squared from both terms. And for the fourth term, we'll cancel r squared sine squared from both terms. This means that the last three terms are all the same. So I'll write out the term once with a multiplying factor of 3 in front. Now, both remaining terms involve 1 over c squared, a multiplying factor of 3, and a common denominator of a squared. So we can just add all the numerators to give us 2a double dot. And if we factor a 2 from all the terms, we can change the 3 in front into a 6. And this gives us the Ricci scalar for the FLRW metric. You'll notice that this Ricci scalar value has a negative sign in front. This is because we're using the mostly minus metric convention. If you're using the mostly plus metric convention, the Ricci scalar will be positive instead. Basically, whatever sign convention you choose, the term 1/2 times the Ricci scalar times the metric should end up having the same sign, since multiplying the metric by -1 has the effect of multiplying the Ricci scalar by -1 as well, and the negative signs just cancel. So we have all the required tensors on the left-hand side of the Einstein field equations. In the next few videos, we'll use the connection coefficients to calculate the paths of free particles in an expanding universe, and also plug these tensors into the Einstein field equations to derive the Friedmann equations, which determine how the spatial scale of the universe evolves over time.